Awesome. Well, thank you very much, Mark. And today I'm just going to walk through a brief history of distributed consensus algorithms and some implementations in Go if you want to play around with them. Um, just as a brief moment of introduction, my name is Jack Zampolin. I'm the product manager at Tindermint and Cosmos. And this is my second GopherCon. I was actually here back in 2017 with a company called Influx Data, which also ran on as a consensus algorithm that I'm going to walk through in this talk as well. Okay, so just a brief overview. What is consensus when we're talking about it with computers? I think we kind of know what it is with people, but with computers, how do you get in computers to agree that x equals 5? That's a very generic way to say it, but how do we get a bunch of computers to agree on a certain state? So, if you try to naively solve this, you might try to do it manually with something like rsync. Now, has anyone tried this before? Yeah, not a great one. We've all been there. Another way to do this is automate that a little bit with kind of an active-active setup, where you have two databases, you're writing to both of them, and maybe you're mirroring writes between them. Now, if one of those databases go down, you then have inconsistent state. That's an issue. Active-passive is potentially easier. You've got one database that's accepting all the writes, and you're mirroring them over to another database that's not accepting writes. So maybe easier, but still very problematic. You can go out there and find active-active and active-passive setups for a lot of the major databases out there in the world now, like Postgres and pretty much everything in SQL. But we kind of need a better way to do this. So in consensus research, computer scientists have been working on this for a while. Published in 1989, Paxos came out and got popularized by a journal article in the 90s. Now, this is broadly used inside of large tech companies. Most of the services that you're querying at Google, Facebook, Microsoft are probably built on top of multi-level Paxos clusters. One of the nice things about Paxos is that it works. You can actually get the computers to agree in a provable and formally verifiable way on a discrete set of state. The bad part there is it's pretty complicated. A lot of folks will implement this as part of their PhD thesis. So you can see a lot of implementations floating around on GitHub with 5 stars and 5 or 6 years ago. But yeah, you can go read the formal paper. There's a number of different variants of this. It's pretty easy to check out online. Another bad part about this is that it needs to run on trusted nodes. So, if I wanted to run a consensus cluster with all of you fine folks in here, any one of you could take down the cluster, and that's not great. Also, failure recovery, a little dicey. Down there in the Go piece, there's a couple of Go implementations of Paxos that I was able to find on GitHub, and that's kind of the tip of the iceberg. As I mentioned, there's a lot more of these things. So the next sort of major type of consensus algorithm that we saw in the world was proof of work. Wait, we're not talking about cryptocurrency, are we? So the Bitcoin white paper came out in 2009. This is broadly used by a large number of cryptocurrencies. And the way it works is basically computers compete with the amount of CPU power they have to contribute the next state to the system. And this is nice because anyone with a computer can compete, and it's very secure against adversarial behavior. So if all of us in here ran some computers and did a proof of work system, we could maintain some state. Now, we might have some problems with forks, which is one of the major issues with it. It also creates arms race-like incentives. If one of us has an incentive to kind of control the ledger and change state in a way that's not great, there'd be an arms race to try to do that. The attackers and defenders have to get more and more CPU power. And that, as you can see, is very, very energy inefficient. And it leads to a winner-take-all security model. So a lot of people theorize that there will only be one proof-of-work system in the world, because if you're just throwing compute power at it, any smaller systems could easily be swamped by the larger system. And that's what we've seen happen in the cryptocurrency world, actually. So in Go, there's a couple of excellent implementations. The BTCD implementation is written by the folks at Lightning Labs, who are working on scaling Bitcoin right now. And if you're interested in learning how Bitcoin works, going through these implementations and picking through the code is pretty fun, actually. So back in the world of sort of non-cryptocurrencies, in 2013, a paper came out called In Search of an Understandable Consensus Algorithm. And this birthed Raft, which I think most folks in this room are familiar with. Who knows Raft here? Yeah, quite a few. So this is used in open source projects like Kubernetes and CockroachDB. It's easy to understand and easy to implement. This is something that I think most of us here could probably read through the paper, look at a couple implementations, kind of wrap our minds around it, see Ben Johnson's Secret Lives of Data, and kind of figure out roughly how the consensus algorithm works. And it's fast. You elect a leader, and then the leader makes updates to the state. And if the leader goes away, then you elect a new leader. The bad thing is you also need to trust the computers in this setup. So unlike Bitcoin, you can only kind of run a few of them, and you got to trust them. And it's a relatively small number of consensus participants normally. And again, failure recovery here, a little dicey. The folks at Cockroach and etcd have been doing a lot of work in that area, but still, I don't know if anyone's ever tried to do it. It's not the greatest. So the canonical implementation in Go is HashiCorp's Raft. There's also a number of PhD students that have gone out there and implemented it with various things. Anyway, okay, a minute. So finally, there's Tindermint, which my company Cosmos developed, and that came out in 2014. This is understandable and implementable. It's a lot like Raft, and there's a bunch of visualizations out there that will explain how to do this. It supports untrusted consensus participants, and it allows the construction of incentivization mechanisms on top of it. Bad thing is, it doesn't support an arbitrarily large number of participants, and performance can be improved. We maintain the canonical implementation in Go at github.com/Tindermint, and yeah. So why am I talking to you about this? Right now, there's a fight for the future of consensus algorithms. Facebook published a paper called Libra. They're creating their own cryptocurrency. They quote us in the first page of that white paper and have made a few modifications to Tindermint and are trying to run a system with 100 banks and large institutions. If we really want a global consensus layer where everyone can participate, we need to participate and build it now.
Thank you, Jack.